Hi friends, the last class we learned about recursive types. Okay, so in this class we'll be dealing with some of the programs that will happen when we declare the dynamic objects. Okay, and so the basic thing that when you declare a dynamic object is that whenever you declare a dynamic object, and if that object doesn't need to be used, then we should deallocate it. Okay, else the space cannot be used by another program. So we have to deallocate it. Okay, so reallocation can be happening in two types. Okay, one is by explicit, the second one is automatic. Okay, reallocation can happen in two types. The first one is explicit, the second one is automatic. Explicit means the programmer himself, as he is allocating the memory, after his use, he will be reallocating. Okay, so in C program, you will be familiar with something called free PTR. Okay, after declaring a node in a linked list, if it is not used, if it is to be deleted, then we use to free it. Okay, so this is one type of reallocation. Likewise, in Pascal, we will be using keyword dispose. Okay, and in C++, we will be using delete. Clear. This is how we will be deallocating the memory, and this is called explicit declaring object. Okay, another way of deallocating is an automatic deallocation. It will be using automatic. It is called as automatic garbage collection. We will be dealing with it in detail later in this session. Okay. Before that, we will be going to a problem called Dangling Reference problem. This is a very important problem. Few times it asked for the university exam, so just understand what a dangling reference program is. Okay, so we'll explain this problem and the program, and we will understand what a dangling reference program is. Actually, dangling reference program means a pointer leaves what the object doesn't leave. Okay, there is no valid object to which the pointer points. So there is a pointer which holds the address, but in that address there is no object. Okay, so that is called dangling reference program. Okay, so we'll be discussing it in using this program. First, we'll start from this program, and we'll move to the first step, that is I equal to 3. So if I am writing in the I equal to 3, what happens is I'll be declaring a variable and I am storing the value 3 to the I. And the address of I be 1101. Now I am in the next step, I am writing in the start PTR equal to address of I. So what happens? The PTR is declared, and in the address I am writing 1101. So this is address of PTR. Okay, this is a function definition. Will be explained while function is called. Okay, so we'll move to the next step, that is cout star p. Cout star p means whatever the value in which the pointer points to has will be displayed. The pointer points to I, and the value of I is 3, so 3 is displayed. Simple. Okay, now what you do is you will be calling function foo. Okay, so the function foo is called. Inside here we know that int n equal to 5, so I am writing n equal to 5. And I have written p equal to address of n. So what happens if the address of n is 2202? Okay, if the address of the n is 2202, then what happens? This 2202 will be stored in PTR. Clear? Right. Now understand that this n is a local object. Okay, n is a local object. It doesn't have a scope outside the function, or it is a local variable. When the function finishes the execution, the variable will not leave after that. Okay, it will be destroyed after that because it is a local variable. Okay, but p, it is a global variable. It is a global variable. Since it is a global variable, it exists even after the local function execution is over. Okay, so p is a global variable, n is a local variable. So when you come out of this function, there exists no n. N will not be there outside this function. but P exists. Okay, so I can write C out star P. But when I write C out star P, what happens is star P has the address of n. Right, star P has the address of n. But here in the outside the function n doesn't exist. So what happens? Star P gives a undefined behavior since n doesn't leave there. Okay, so this is a pointer which points to an object which doesn't leave. So this is called a dangling reference. Hope it is clear. Okay, now we'll be explaining one more program. Okay, so this is another program. So in this, it is written in this star p equal to new. Okay, so star p is declared. Okay, star p is declared, and to which it points, I am storing 3, star p equal to 3. So this is dynamic memory allocation. Okay, this is dynamic memory allocation, and the star p equal to 3. Okay, so I have written like this. And if I am displaying star p, what happens? Displaying star p, 3 will be displayed. Now if I am deleting p, what happens? Or to point over point memory location point of p points to, it will be deallocated. So 3 doesn't exist. Okay. Now if I am writing C out star p, so this is since C out star p will be having the address of 3, but 3 is already deallocated. So it has a reference to an object that doesn't leave. So this is also called as a dangling reference program. Hope it is clear. Okay, so dangling reference program means there is a reference to a object which doesn't leave. So this is called dangling reference program. So we discussed two, one explained using a local variable, the other one explained using a dynamic variable. Okay, okay, this is clear. Now we'll move to the next part, that is garbage collection. Okay, so we know that explicit reclamation is possible, but instead of that also we'll be using something called garbage collection. Okay, explicit reclamation of heap objects may create bugs. Okay, some bugs are, one is dangling reference is one bug, as we have seen in the last program. Here we were using delete p, which is explicit reclamation, and as a resultant of it, a dangling reference happened. Okay. Next one is memory leak. What do you mean by memory leak? Memory leak is something like the reverse of dangling reference. In that, actually the object exists. Okay, object exists, but there is no pointer which points to that object, or there is no reference to the object, so that the object cannot be accessed. That is called memory leak. Okay, for example, if I have declared PTR, let it be so. Okay, so dynamically I have allocated one memory. Okay, so let it be 1101. Dynamically I have allocated a memory using PTR, so PTR will be holding 1101, so that I can access this memory using PTR. If I am again writing PTR equal to m alloc or something, size of int, what happens? This memory will be there, but again what happens? A new memory will be allocated. Let the address of this be 2201, and the PTR will be having 2202. So the PTR will be having 2202. That means it will be pointing to the second memory. Okay, here what happens? Here the object 1101, the memory space 1101 is allocated. It can be used, but it cannot be used since no pointer will be pointing to that memory location. Okay, so that is called memory leak. The reverse of dangling reference. In dangling reference, the object doesn't leave, but the reference exists. In memory leak, object leaves, but there is no reference of memory. Okay, so what happens? The space or the object cannot be used since there is no reference to it. Okay, so that is called memory leak. So these are the two side effects of reclamation of explicit reclamation. Okay, one is memory leak, second one is dangling reference. So to remove that or reduce this, we'll be going to garbage collection. Okay, garbage collection in this, the compiler itself will be doing all the collection. Okay, so we'll be moving to different uh, type of garbage collection. The first one is reference count. The first one is reference count. Okay, so we'll define what a reference count is. Okay, so in reference count, what we'll be doing is we will be reducing the memory leak. Okay, so we'll be reducing memory leak. Okay, we'll be finding out the objects which are not referenced, and the compiler will be reallocating. Okay, in reference count, all the garbage collection, what happens is the compiler will be finding out all the objects that are not referenced. Okay, clear. So in garbage collection, what the compiler does is it will find out all the objects that are not referenced, and it will reallocate that objects. Okay, since it cannot be used, they are called the useless objects. Okay, in reference count, it says that when no pointer exists, okay, when no pointer exists for an object, it says to be useless. If there is no pointer to that object, it is said to be useless. Okay, okay, okay. So what happens is when an object is created, okay, when an object is created, together with it, in this, a reference count will be created. Okay, so there is, when an object is created, with it, another reference count is there, attached. And a reference count is attached. Okay, so if an object is created with a reference, automatically we know that when an object is created, there will be a reference to that object. So the initial value of reference count is 1. Okay, so if I am writing ptr equal to malloc size of int. If I am writing a step like this, what happens? A memory is allotted. The ptr will be holding. ptr will be holding what? The address of this. ptr will be holding the address of this. Clear. So when an object is created, already it do have a reference. Okay. So the reference count will be initialized as 1. And I am copying the reference. For example, if I have another pointer ptr2, and if I am writing ptr2 equal to ptr1, so here ptr1. So if I am writing ptr2 equal to ptr1, okay, ptr2 equal to ptr1. So what happens? The reference is copied. So actually, this thing has 2 references. You do have 2 references. Okay, so when the reference is copied, the RC will be incremented. Okay, when the reference is copied, the RC will be incremented. And if one of the reference is deleted, okay, or if it is PTR is changed from PTR1 to some another value, if I am writing PTR2 equal to ml of size of int. Okay, so if I am changing the reference, okay, if I am removing the reference, okay, or if I am removing the reference, what happens? The reference count will be reduced from 2 to 1. Okay, the RC will get decremented. So when the reference is copied, RC will be getting incremented. When the reference is removed, then the value of RC will get decremented. So actually RC will be giving out the number of live references of that object. And when RC becomes 0, when RC becomes 0, what happens? When RC becomes 0, that means there is no live references for that object. That means that object is unused object. That object is unused object. Clear? So what happens? This compiler automatically reallocates this memory. If the reference count is 0, then the compiler automatically reallocates the memory. So this is how the garbage collection using reference count works. Clear? I hope it is clear. Okay. Now what is the disadvantage? Okay, consider a allocation like this. Okay, so there is a variable stooks. Okay, there is a variable stooks, and there is a linked list. Okay, this is a circular linked list. Okay, circular linked list, and this is the reference count. Okay, so actually stooks is pointing to the first node, and the last node is also pointing to the first node, so the reference count is 2. First node is pointing to the second node, so the reference count is 1. The second node is pointing to the third node, so the reference count is 1. Clear? So this is a circular linked list. Okay, so this is a circular linked list. Now what happens when I just disconnect this connection? That means if the stooks, the variable stooks points to null. Okay, the stooks is null. The stooks point to null. It doesn't have any reference. It doesn't point to anything. What happens? It's actually what happens is this variable this node do have one reference. This variable also do have one reference. The reference count is 1. This node also have reference count as 1. Okay, since the reference count is 1, the garbage collector won't be reallocating these nodes. But actually, in this scenario, these nodes cannot be accessed from the outside world. Okay, from the outside this 3 nodes, none of the nodes cannot be accessed because there is no external reference. Only if there is an external reference of a program, these nodes can be accessed. There is no external reference. In the program, we doesn't have the address of any of these 3 nodes. So we cannot access these nodes. Okay, only if we access one of these nodes, we can move to or we can traverse to all those nodes. But there is no reference of any of the nodes outside the program, outside this. Okay, so what happens? This actually is a memory leak, but this will not be solved using reference count. Okay, this will be a memory leak, but this won't be rectified using reference count. Clear? Hope it is clear. So this is one of the disadvantages of reference count. Okay. Now the other method is tracing collection. Okay, so there are 2 methods. The first one is reference count. The next one is tracing the collection. Okay, so actually what happens is the compiler will move out to the allocated variable to check whether there is a reference or not. Okay, if it do have a reference, then it will be used. If it doesn't have any reference, it will be deallocated. Okay, that is a tracing collection. In reference count, it do have a variable called reference count, and it will be if the reference count is 0, then the variable or object will be deallocated. But in tracing collection, the compiler himself moves to all the data structures that are present in the heap structure, and so that if it finds some unused memory blocks, it will be deallocated. If it finds the block is useful, then it will be saving. It won't be deallocating that memory block. Clear? So that is tracing collection. And in tracing collection, there are 5 methods. The first one is mark and sweep. Second one is stop and copy. Third one is pointer reversal. Fourth one is generational collection. And the fifth one is conservative. Sorry, this is conservative. Okay, conservative collection. Clear? So these are the 5 methods that comes in trace collection. Okay, clear. So we'll move to the first one, that is mark and sweep. So in mark and sweep, what happens is the collector moves from one to other data structure. Okay, so you have a memory, right? You have program variables. Okay, so we have program variables. So if there will be a point PTR, if there will be something called PTR2. So these all are the program variables. Okay. So what does the compiler do is the compiler will start from the program variable. It will start from the program variables. Okay. It will start from the program variables. It will move to the heap. Okay. It will move to the heap data structures. So whatever the memory blocks which are dynamically allocated is accessible from this program variables will be marked. Okay, whichever the variables, whichever the memory blocks that can be accessed from the programming variables, the variables that are in the program, that will be marked. Okay, so a variable will be attached to that block and it will be marked as useful. Okay, so when it covers all the program variables, it will travel. If it travels all the data structures from the program variables, what happens? The compiler understands which all blocks are useful because all the useful blocks which were traversed are marked as useful. So the compiler will understand which all blocks are useful. Okay, so what happens? It will take out the useless blocks and it will deactivate. Okay, that is the process of mark and sweep. Okay, so mark and sweep has three steps. The first one, collector moves to all the heap blocks and mark as useless. Okay, first of all, it marks every block as useless. Okay, then it recursively explores all the structures in the program. Okay, all the structures. So it will be using the program variables and it will move to all the structures, all the heap structures in the program. And if it gets into a block, it will mark it as useful. If it gets into a block, it will mark it as useful. Okay, so to all the blocks in which the compiler can reach, it will mark as useful. Okay, so all other blocks remain useless. Okay, after traversing all the program variables, what happens? It will get the list of useless blocks, right? So what happens? The collector will free all the useless. Hope it is clear. That is mark and sweep. Okay, now the disadvantage of mark and sweep. Actually, mark and sweep is a recursive call. Okay, first thing is mark and sweep. It traverses objects recursively. It is a recursive call. So it needs stack object. The first disadvantage is it needs stack. Since it is a recursive call, it requires stack. So that is one of the disadvantage. And another disadvantage is uh, the normal execution of the program will be stopped. Okay, so the normal program will be stopped and the garbage collection happens. After garbage collection happens, again it resumes the normal working of the program. So actually we are adding a new task to the processor. We are giving new task to the processor. Garbage collection is new task. So we do have a lot of tasks to perform. Together with that, we are giving another task. That is a garbage collection process. Okay, so it is another work for the processor. Okay, so we need to suspend all other works to do this garbage collection. So it's time consuming. Okay, now the next one is as a result of this mark and sweep, the blocks, the used blocks will be like fragmented. It will be small fragments. It will be in the form of small fragments. Okay, it will be separated by all the used memory will be separated by small unused pieces. So it will be in the form of small fragments, which is the disadvantage of mark and sweep. Okay, so one is that GC garbage collector need to stop all other works for garbage collection so that it can execute garbage collection. The second one, it will just split the used memory into small fragments. Okay, so these are the disadvantages of mark and sweep. Next one is pointer reversal. Okay, Already I told that mark and sweep is a recursive and it do need some stack implementation. So it do need more memory. Okay, sometimes when you are doing this, when you are doing the garbage collection, when the memory is low, then only when the memory is low, you will be doing the garbage collection. And to do garbage collection, if you need to allocate some memory, that means it it is not practical, right? Okay, you do garbage collection when you need some memory, when you don't have memory, and for garbage collection, if you need more memory, that won't be practical, right? So that's a disadvantage of mark and sweep. Okay, yeah, it recursively go for the data structure. It recursively traverses the data structures. So since it is recursively traverses the data structure, it do need some stack. Okay, so it is not possible. So the other way is pointer reversal. Okay, so pointer reversal actually deals with how to traverse data structure, how to traverse a data structure without using a stack. This is how pointer reversal happens. Okay, traversing a data structure without using a stack. Okay, so in pointer reversal, what happens is, okay, listen here. Uh, this this set is used to traverse the pointer. Okay, so we do have two parts. First one is the previous, the second one is current. Okay, so this is the starting node. R is the starting node. Okay, so what happens is the main problem of traversing a tree or traversing a data structure is that if I am moving from R to T, okay, here you can see that there is a pointer from R to T, but after traversing T, there is no possible way to move from T to R. That's why you are using a recursive call for traversing a tree, right? So you are using a recursive call to traverse a tree because if you are traversing from R to T, okay. For example, if I am just traversing this in order, as in order, okay, in order it will be left to parent and right, right. So first I need to traverse S, so I'll be moving from R to S. So now I am in S, and if I need to traverse, and if I need to go for the next node, then I need to go back to R, right? But since there is no linkage between S to R, that traverse is not possible. That's why you are using either to traverse, you will be using a stack or you will be using the recursive function. Both working is the same. In recursive function, it uses stack. So you can use either recursive function or you can directly use stack, whatever it means. Okay, so that traversing is not possible. So what you do is, instead of this, you will reverse the pointer. You will be reversing the pointer. Okay, reversing the pointer means, so here you know R to T, there is a pointer. So when you are traversing from R to T, what you do is you will just reverse the pointer. Okay, you will just reverse the pointer. Likewise, when you move from T to U, what do? You will reverse the pointer. When you move from U to W, you will reverse the pointer. So that when you reach W, you can move back to U. Likewise, when you reach U, you can move back to T. When you reach T, then you can move back to R. Clear. So what you do is you will reverse the pointer when you traverse. Okay, so what happens is, I'll just explain. Okay, so here it is R. When I'm moving to R to T, if I'm moving from, actually the pointer is like this. If I'm moving from R to T, what happens? I will reverse the pointer so that after traversing T, I can move back to R. Okay, R to T. From T, I'll be moving to U. So there is a pointer exists from T to U. When I traverse to U, what happens? I will reverse the pointer. It will be like this. Clear. From U, I will be traversing to W. So what happens? To U, there is a pointer to W, but when I am traversing, I'll be using. I will be reversing the pointer. Okay. So the data structure will be like this. After traversing W, I need to go back to U, right? After traversing W, I need to go back to U. So when I go back to U, what happens? Again, I will be reversing the pointer so that the data structure will be in the same as that of in the starting. Okay, after traversing U, I have to go to T. So what happens when I move to T? Again, I will be reversing the pointer. So it will be like this. After traversing T, I will be moving to R. So what happens? I will be again reversing the pointer. So R will be here. Again, I will be reversing the pointer. So the data structure remains the same after the traversal. After full traversal, the data structure will be same because it will move to and fro two times. Okay, so first movement it will be reversing the pointer. In the second movement also it will be reversing the pointer. That means pointer will be in the correct direction after movement. I hope it is clear. Okay, so that's shown here. Okay, so here also you will be just reversing the pointer, again reversing the pointer, again reversing the pointer. When you traverse back, again you will be reversing the pointer. Remaining, you will be getting the initial direction. So in this, what you will do is you can traverse to all the nodes in the tree or graph or the data structure that you have, but you are not using tag or any recursive function. Clear? So this is called pointer reversal. Now, the disadvantage of pointer reversal is that uh, sometimes the GVC will reach somewhere and it will get stopped because the data structure is invalid. And in middle of some data structure, it need to get stopped. Okay, due to some invalid data structure. Okay, so that is a disadvantage of pointer reversal. And also we know that for this also we'll be using an extra bit that need to take care of all the objects we have processed. Okay, we will be marking it. If you are traversing a node, we will be marking it. And make sure that the node is useful, we will be marking it. And all the useless node is deleted. Okay. So for marking as useful and useless, we will be using an extra bit. So that is a disadvantage of a pointer traversal, which is also the disadvantage of mark and sweep also. Okay. Same. Mark and sweep also use an extra bit for keeping track. So it can be taken being told that it is a disadvantage of mark and sweep. Okay. Next one is stop and copy. Okay, in stop and copy, what happens is actually the memory is there. So I'll have the memory. So the heap memory will be divided into two halves. Heap memory will be uh, divided into two halves. Okay. So there is first half and there is second half. Okay. And all the allocation will be happening in the first half. All the allocation will be happening in the first half. Okay, so if I am allocating a tree, or the tree will be allocated here, the graph will be allocated here, or all the allocation, all the memory allocation of the recursive types will be happening in here, in the first half. Okay, when this first half is full, then what happens? Then there is no space for allocation. So what happens? Then the garbage collector move through the data structures. The garbage collector move through the data structures. Then it finds out the useful data structures. Finds out a useful data structure and it will copy to second half. So if this data structure is useful, only that data structure is copied. If this is not used, it doesn't have any references and all, it is not used. Okay, so that data structure will not be copied. Only the useful data structure will be copied to the second half. After that, it will clear the first half. Okay, so it will deallocate all the data structures in the first half. Then again, what happens? It will copy back whatever data structures is used to the first hacker. Okay, so we'll delete from here and we'll copy the useful data structure to here. So in first half, after this process, only the useful data structure will be. Okay, this is the thing called stop and copy. Okay, this is clear. So in this, the heap memory will be divided into two equal halves. All the allocation will happen in first half. When the first half is full, then the GC, that is the garbage collector, will be finding out all the useful data structures, and all the useful data structures will be copied to the second half. First half will be cleared, then the useful data structures that are stored in the second half is copied back to the first half, and the execution continues. Clear. Again, if the first half is filled, then again the useful data structures will be copied to the second half. First half will be clear, then the data structures will be copied back to the first half, and the execution continues. Okay, so this is what happens in stop and copy. Hope it is clear. The disadvantage of stop and copy is that if you have 1 GB of memory, only 500 MB can be used, because 500 MB will be using for garbage collection. Only one half of the memory can be used. So that is a big disadvantage. And also you are doing two copy activity. Okay, copying from first half to second half and back from second half to the first half. So you are doing two copying activity, which will take time if the application is large. Which will take time if the application is large. So it is time consuming. Also the space you cannot utilize over whole space. Okay, so that's a stop and copy. Next one is generation collection. Okay, in generation connection, what happens is, instead of dividing them heap into two halves, in this the heap will be divided into small halves, multiple halves, multiple regions. It will be divided into multiple regions. Okay, so the heap will be divided into multiple regions. The heap will be divided into multiple regions. Okay, and in this there is a assumption that the dynamic objects are short-lived. Okay, mostly the dynamic object will be short-lived. There is something assumption like that. Okay, so in this what happens is these regions, okay, are given some age. Okay, these regions are given some age. For example, let it be 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Okay, so these are the, let this be the ages. So 1 is the youngest one and 5 is the oldest one. Okay, so the heap is divided into many regions and the regions are given some age. Okay, all the allocation and deallocation happens in the youngest age, the region with the youngest age. The region with the youngest age is 1. Okay, so all the allocation and deallocation will happen in region with youngest age. Okay, when the space is and what happens is, if a data structure is stored in here for a long time, okay, in the younger stage for a long time, if a data structure is stored here for a long time, then it will be copied to the older age. Clear? I hope it is clear. All the allocation happens in the younger age, and if the data structure stays here for a long time, it will be copied to the older age. Okay, if it stays here for a long time, it will be copied to the higher older age, more older age. Okay, likewise it will be copied. Okay, and when the space is low here, so here is the place where the direct allocation happens, right? And if the space is low in the younger region, okay, if the space is low in the younger region, what happens? It will less deallocate the spaces which are not allocated now. Okay, the spaces which are not allocated now will be reallocated because it is not used. The used data structures are already copied to the older ages, right? So the data structures which are here, the data structures which are here and which are not allocated now are useless. Okay, so it will be deleted. Okay, so what happens is in generation correction, the memory is divided into many regions and they are termed in the form given some ages. Okay, and the memory allocation happens in the younger age. If it stays for a long time in the younger age, it will be moved to the older ages. Clear? We will move to the older ages. And the memory is, if the memory is full in the younger age, then it will be allocated the data structure that is not allocated now. Okay, it is not allocated in the present, it will be deallocated because it is not used. Okay, so you will get space. So that is called generation collection. Hope it is clear. Next one is conservative collection. We are not the process of conservative collection. We are not specifying here. In conservative collection, many languages won't be having a garbage collector as it has. It doesn't have a garbage collector. Many languages won't be having a garbage collector. So actually, in conservative collection, there will be some libraries. Okay, there will be some libraries which can be used by any languages. There can be libraries which can be used by any languages for garbage collection. Okay, so what happens is it doesn't have any cooperation with the compiler. Okay, so it doesn't have any cooperation with the compiler. So those are libraries which can be used for garbage collection for the languages which doesn't have a garbage collector as for its own. Okay, so that is called a conservative collection. The main disadvantage is that since the compiler doesn't cooperate, the garbage collector need not know which all are the pointer or which all are the data structures, which type of data type is that. That's all the garbage collector won't understand. Okay, so the garbage collector will be taking all as a integer or character nodes. Okay, so it would be difficult for the garbage collector to find out which type of data it is, and also might uh, think that some of the structures is a pointer and may leave uncollected. Okay, some of the structures is pointer and may leave uncollected because it doesn't know what actually the data structure is, which type of data structure it is, which type of node it is, which type of value it stores. Okay, that's all the garbage collector doesn't know. Okay, sometimes there might happen that the pointer, it will think that some data space is for pointer and it will not collect the data or it will not clear out the data object. Okay. It happens. And also for the garbage collection process, the processor need to stop. Okay, for the garbage collection process, the processor need to stop all other works and need to do the garbage collection, and after that it need to go. Okay, so that's about conservative collection. Okay, so that's all about today's class. I hope you understood about the garbage collection techniques. Okay, actually garbage collection will be having two types. Okay, the first one is reference count, the second one is tracking method. The tracking method you went to five. Okay, mark and switch was there, stop and wait was there, recursive means pointer reversal was there. Okay, generation collection was there, stop and go key, and conservative collection. All these were the tracing methods that were used for reference. Hope you understood. Thank you, and make sure that you learn about memory leak and dangling reference, which are sure questions from this subject, and also the garbage collection technique, that is also very important. Okay, thank you. Have a nice day.